Conservation of mass. There is no new matter. In a chemical reaction, matter is not created or destroyed. So by chemical reaction, we are excluding nuclear reactions. In nuclear reactions, you can convert matter into energy and energy into matter, and all kinds of crazy, funky things happen. In this building, we don't do anything that's nuclear, okay? It's just chemical changes. So with the Lego analogy, a chemical change is playing with Legos with your hands. A nuclear change would be taking the Legos out to the garage and using a blowtorch on them or a hacksaw and cutting them up. That's not normal stuff. That's crazy stuff. So in a chemical change, all the atoms that you start with are all the atoms that you end up with. When you build with Legos, if you start out with 50 red 2x4 pieces, when you're done playing with them, you still have 50 pieces. No matter how you rearrange them, the pieces you started with are the pieces that you end up with. So matter's not created or destroyed. So an example of this is, back to that butane lighter. So if we burn butane in that lighter, the butane is going to react with oxygen. These are the reactants, and they're going to undergo a chemical change and turn into carbon dioxide and water. Well, you said nothing was created or destroyed. Well, all we did was we took apart the little structures that we'd made out of the Legos that were the butane and the oxygen, and we took those blocks and we put them together in a different combination. All the atoms we started with are still there. All the mass that we started with is still there. So if it was 58 grams of butane and 208 grams of oxygen, the total mass of the reactants is 266 grams. If you collected the carbon dioxide and the water that was given off, they would total 266 grams. Matter doesn't get created or destroyed. When we have a situation where it appears that our products weigh less than what they started with, it's usually because we're overlooking something. So you take a big log and you stick it in your fireplace. This is a big, heavy log, and you burn it. After it's all done burning, what's left? Ashes, right? Are ashes heavy? No, they're really light, and if you blow on them, they go all over the place and make a big old mess. Did matter disappear? Did we destroy matter? No. When we burn the wood, most of the wood goes into carbon dioxide and water in the gas state, and those go up the chimney, and they go off into the atmosphere. Are they gone? Well, they're not in our presence anymore, but if we captured them, we would find that the mass of the products equals the mass of the reactants. It's a very important idea. So here's a question that typically seems to be very difficult and way too hard for this point in the semester, but it's not. This is just about conservation of mass. So suppose 12 grams of natural gas combines with 48 grams of oxygen in a flame. The chemical change produces 33 grams of carbon dioxide. How many grams of water form? Well, let's make a little picture here. What do we have? We have natural gas and oxygen. We're just going to use words because we don't know about chemical formulas yet. Gas and oxygen, and what do they make? They make carbon dioxide and water. The problem's telling us that. So carbon dioxide and water. Well, it's saying that we've got 12 grams of the gas, 48 grams of the oxygen. And it's saying we made 33 grams of carbon dioxide, and it wants to know how many grams of water. Conservation of mass says that the total here, which is, 60 grams, has to be equal to the total here. Some of you were able to look at that and just, well, you just take this and this and you subtract that. Sometimes it's helpful to draw a picture. I would consider this a picture. So then what's this? Well, it's 33 plus what equals 60? 27? So there must be 27 grams of water produced. So if you see a problem like that on the exam, that's supposed to be an easy problem. Okay, it doesn't involve huge chemical calculations or anything. It's just adding and subtracting. Any questions about that one?